Well, you kind of want to be like standing there, no, and then you realize, right, because they don't know paper. It's like, sure, we're trying to get this looks like that. So believe in that. Oh, well. That really happened. It's only 2 pieces of paper. No, without flashing. We're going to make the same joke this morning on the Riley without me saying anything.
Hey everyone, so Friday we did 2 things, right? Our 2 big topics that we covered Friday was being able to use f of x, f prime, f double prime to create a fuller picture of the graph. There's information that we can gather from all 3 functions, but they all produce different but related information connected to a graph. And then the second topic we talked about was how do we look at a derivative graph and be able to pull information about the original graph. And basically everything that is on the graph is slope related, so it's not the shape of the location graph that we're used to seeing. And being able to interpret that is going to be a big part of what we need to do. So today we're just going to revisit those 2 subtopics. And then tomorrow we'll do our last topic, which is optimization. Okay. So we did number 1 in class on Friday. So let's go to number 2. So number 2 is a rational function. It's a little bit more involved, but the idea is the same. We're going to gather information from f prime, from f of x, from f double prime, and we'll put all that information together to get a picture of the graph. So first up is, what information can we gather from the original function?
Vertical asymptote.
Okay, good. What else?
X intercepts.
X intercept, good. All right, so how do I find x intercept off of a rational function? Where do I look?
Numerator.
Numerator, okay. And the vertical asymptote? Denominator, okay, good. So we're just kind of extending from Friday, right? Friday was a little bit easier. There was no denominator, so we only have to look for x-intercept, but now we have a denominator. So, okay, so we know that x-intercept comes from the numerator. I can set the numerator of the function equal to 0. To find vertical asymptote or holes, but I'm going to say vertical asymptotes for now. We set the denominator of f of x equal to 0. And there's one more thing that we haven't talked about, and that's horizontal asymptotes. Horizontal asymptotes we can find by comparing degrees, number of limits approaching infinity. So comparing degrees, and then ratio of coefficients. So all this is helpful information because they're going to kind of give us some anchor points, give us some boundaries for our graph, and so we know when we sketch it where to kind of where our graph is going to go. So let's find x-intercepts first. So we said numerator equal to 0, right? So numerator equal to 0. Divide both sides by 2, take the square root, we get x equals 0. So that's just 0, 0. That's my x-intercept. Denominator equal to 0. I can factor that, or I can solve for x. So those are the location of my vertical asymptote. And there's one more piece of information, and that is horizontal asymptote. So if I compare degrees, my degrees match. So that means I can take the ratio of the coefficients. What's the ratio of the coefficients here?
1.
Well, we look at the, yeah, 2 is in front of the x squared. What's in front of this x squared? -1. So 2 over -1 is -2. So that is our horizontal asymptote location. So essentially we're doing this. We're doing limit as x approaches to infinity of 2x squared over 9 minus x squared. We see that's 2 over -1, which is -2. So that is telling us where our horizontal asymptote is located, y equals -2. All right, so we're going to put those pieces of information onto our graph. X-intercept, we know the graph's going to go through that point. Vertical asymptote, we know the graph will get close to these vertical lines without ever touching them. So dotted line here. And then horizontal asymptote at y equals -2, we know the graph is going to flatten out as it exits towards these lines, but it'll never touch these lines. Well, maybe in between, but not as we extend past the graph. All right, so that's all the information that we need from the original function. So now we're going to go to f prime. F prime is where we find the derivative. Slope sine line, first derivative test. All right, so what's involved here if I want to find f prime? Okay, quotient rule. So I'm going to set it up and see if we can fill this in. Okay, f prime. Thanks. Clean up, but we got to be careful how we clean up, right? We can't do this, right? This is not going to work. We're going to have to spend the time to expand this out, distribute. Oh, just x side. Okay, any questions so far? F prime. Slope sine line. And where do we look to populate slope sine line?
Numerator.
Okay, numerator. But also denominator as well, right? Let's talk about both of these locations. If I set the numerator equal to 0, what information does that provide for me?
0 slope.
Okay, slope 0, good. If I set the denominator of f prime equal to 0, undefined slope. So that's a very vague term, right? Undefined slope, it could be a sharp turn, it could be vertical asymptote, it could be a hole. But we already gathered that it's a vertical asymptote, so we know it's going to be a vertical asymptote. Now, we know that there's no chance of it being a max or min on the f prime sine line, but we still want to include those critical points because they help separate our intervals of increase, decrease. So So just like before, we're going to set the numerator equal to 0. We'll set the denominator equal to 0, but it's just a different set of information, right? Because it's coming from a different function. So just for context, we know that the numerator is giving us a location of slope zeros. Denominator is giving us information slope undefined, which in this case is going to be a vertical asymptote because of what we determined from the top. But all three numbers are going to go onto my slope sign line. We're going to choose values in each interval as test points, and we're going to plug into f prime. So I'll plug -4 in for x. I get a negative over, let's see, denominator squared, so it's always going to be what? Positive. So negative over a positive is negative. Second test point. Good. So negative over a positive, still negative. One in for x, I get a positive over a positive. Plug 4 in, positive over a positive. All right, any special points that we can specify here? Anything we can categorize?
0.
0 is a what?
Relative minimum.
Minimum, yeah. We know it's a point of slope 0, and then with the additional information of the arrows, we know that the graph is falling followed by rising, so relative min. We know there's a y value attached to that point. If I plug 0 into the original function, I get 0 over 9, which is 0, same as the x intercept. So relative min is going to kind of double as the x intercept as well. Okay, so I think that's all the information that we need from f prime. We'll move on to f double prime. So how do we get to f double prime? Good, quotient rule, but there's something else that's going to make this a little bit more complicated. Yeah, there's that chain rule portion. Okay, remember that we look at the parentheses, right? Parentheses, if it's over the entire problem, we know chain's going to come first, but if it's only over a portion, we know quotient is going to come first. Quotient is going to have a larger impact over the problem, so larger impact gets applied first. And then once we're inside quotient, then we can see how the chain rule comes in. Okay, so let me label my parts here. All right, so f prime, g function, back to f. All right, g prime, this is where we have that function within a function, right? So this is where chain rule is going to get used. So there's outside, there's inside. So outside is the parentheses squared. Inside is the 9 minus x squared. And we know how we do chain rule, right? We take outside's derivative and we follow it by inside's derivative, but we place them next to each other, right? Not inside one another. All right, so what's outside's derivative?
2 parentheses.
times the inside's derivative, negative 2x. A little squished here. So the 2, the 9 minus x squared, the negative 2x, all that is going to be the derivative of the g prime because of my chain rule. Okay. All over my denominator squared. My denominator is already squared. So if I squared another squared, that means I have 2 exponents multiplied together, so to the 4th. All right, take a look at what we have so far. Any questions? Okay. Okay, we want to clean this up so that we can actually find some critical points, and the critical points are going to be populating our second derivative sign line. But we got to be careful how we do it, right? Again, I know it's tempting to try to start canceling stuff out, but that minus is preventing us. So we have to clean all this up, but now this is messy, right? Having to FOIL all this out, distribute the 36 through. We do have a shortcut, but the shortcut is going to be involving common factor, okay? Not canceling out, common factor. So let me show you what that looks like. Imagine we have these two as separate terms. So I'm going to treat this like a messy collection of terms, and then I have a second collection of terms here. Okay, I could start merging things together, but I want to find common factors. So if I can leave everything separated, it's easier for me to pull, to compare and match what I can take. So here's the thing: what we can do, if we can pull common factors from those two extended terms, then it speeds up the factoring process because if we take out common factors, the remaining expression will go in its own set of parentheses, and those will just combine a lot faster than having to expand everything individually. Think of these as two subcategories or two separate terms. What do you see as common? What's shared between these two terms that I can easily pull from both?
9.
Okay, but 9 is part of what?
9 squared.
Yeah, 9 minus x squared, right? So I can take one of the 9 minus x squared out. All right, there's 2 here, there's 1 here. I can take one of them out. Good. What else is shared between these two terms? 36. So I can take a 36 and a 9 minus x squared from both terms, and that will allow me to condense my factoring, speed up my factoring process. So I'm going to take my common terms out. And then my leftover is going to go in its own set of brackets. So let's say I took a 36 and one of the 9 minus x squared out. Okay, what am I left with? There's still a leftover what?
1 squared.
Well, these are 2 minus x squared, right? So I have another set of 9 minus x squared. Do you guys see that? Okay, so I take these 2 out, but I still have a leftover of 9 minus x squared. Okay. So my second set, if I take out a common factor of 36 and a 9 minus x squared, what is the resulting value that's left over? I got an x, I got a 2, I got a negative 2x. So I can multiply that together to be what? Yeah. All over 9 minus x squared to the 4th. You see how this kind of speeds up the process a bit, because this is already factored form. If I combine these together, then I have exactly what I need to move forward, rather than having to FOIL this out, distribute 36 through. All right, it's faster this way. All right, this can combine, right? By some like terms there. So here's my second derivative factored form. Actually, I'm going to put this a little below here. Two negatives cancel out. I get 9 plus 3x cubed. Sorry, 9 plus 3x squared. Okay, this is a lot cleaner than what we started with, but there's actually something that we can do to clean this up even further. What can we do now that we couldn't do at the beginning? Yeah, we can take out 9 minus x squared here, but we couldn't do it here because there's a minus sign, right? But now there's no addition, subtracting, separating any of the terms, so now we're free to take things out without breaking any of the algebraic rules. Okay. From the second derivative, we can gather information about point of inflection. We can find where concavity doesn't exist. Same thing, right? We're going to look at the numerator, look at the denominator, set equal to 0, find our critical points. So we're getting the same thing from the denominator, right? We're getting 3 and -3. But if I set the numerator equal to 0, is anything going to come out of this? What do you notice? Is that a real number? So no real number, that means there's no critical point here, or no solution here. At least not from the numerator. We still have 3 and -3, so we'll place that onto a second derivative sign line. I'm going to put that up here so we can have it next to the f prime sign line. So 3 and -3, no 0, right? Just -3 and 3. I'll choose test points. -4, 0, and 4. I'm going to find my second derivative function and plug in and test and see if I have concave up or concave down. -4 into the numerator, I'm always going to get a positive value. -4 in the denominator, I get 9 minus 16 cubed, which is negative. So positive over a negative is negative. So second derivative, that's concave down, right? Okay, 0 into the second function, I get a positive over a positive, so concave up. Plug 4 in, positive over a negative, so that's negative, that's concave down. So we're going to put, based off of this information, we're going to try to sketch our graph. Now look at the concavity sign line here. There's a change in sign. So can we call these points of inflection? -3 and 3?
Yes.
Normally we would, but what do you know about 3 and -3?
They're also vertical asymptotes.
Yeah, so this tells us just be careful, right? Here, I know you're looking at that and thinking, okay, there's a change in concavity, but if the graph doesn't exist there, then there's no point of inflection, right? The graph has to exist there. We know there's a break here, so. Okay. Now, if we start off with some easier information, is we can look at the fact that there's a relative minimum at 0. Our graph is going to be concave up, and the asymptotes kind of help give us some idea as to how far our graph is going to extend. Okay. To the left of -3, we want the graph to be decreasing, but maintaining concave down. And we know it has to be worked within the boundaries that we have in front of us. So the only place it's going to fit is here, right? Negative slope, concave down, and the asymptotes are going to play a role in terms of the graph getting closer to it as it exits the graph. Okay. On the right side, we want positive slope, we want concave down, so the only way we can get positive slope concave down is the graph looks like this. The only place that's going to fit alongside our asymptotes is if the graph looks something like this. Okay. You can use your graphing calculator to get a picture of this. You can also go to desmos.com, online calculator, graphing calculator, which will give you that picture as well. Okay, so this just highlights the, what we did with number one, but it's a little bit more involved, right? Number one, we didn't have any vertical asymptote, any holes, any horizontal asymptote, but it's the same idea, right? Function, f prime, f double prime, they all provide information about the graph, just a slightly different set of information. Also, this is more involved because we have to go through more complex derivative rules, quotient rule and quotient and chain. Okay. So the second topic that we did on Friday was being able to look at graphs from a derivative perspective. So I think we did number one. I think we talked through number three, but I'm going to talk through this again. Okay. I'll start from scratch with this one, just talk through it, because after I go through this, I want us to try number four, and if we have time, I have another graph. I just wanted to get some reps in with derivative graphs, being able to look at a derivative graph and gather all the information that we need to gather. Okay, so first thing is, whenever you're looking at a derivative graph, just understand that what you see in front of you is not the original graph. Okay. So I know this looks like a max, that looks like a min, this is increase, decrease, but this is not the original graph, right? So we're trying to gather information about the shape of the original graph, which is not this one. But it's related. So to help us remember, or to help us focus in on what we're looking at, first thing we do is let's go ahead and label our derivative graphs. Let's label the above as positive slope, label below as negative slope, and then indicate anything on the x-axis as slope 0. Next step, go ahead and find your x-intercepts and place them onto your slope sign line. So I have -4, I have -2, and I have 1. And then we want to be able to identify what is the slope behavior in each of these intervals. I know this looks like a positive slope to you, but you see that to the left of -4, the graph is obviously below the x-axis, so the original graph is actually going to be showing negative slope. So we're going to indicate that with negative slope. Between -4 and -2, you see that my f prime graph is above the x-axis, so that's going to translate to a positive slope on the original graph. Negative slope, sorry, below the x-axis is in the negative region, so negative slope. Below the x-axis, in the negative region, negative slope. So now these arrows are going to be helpful because these arrows is going to mimic exactly what our graph will look like. Our graph is going to have a relative min at -4, a relative max at -2, and then a neither at 1. Okay. I sketched the graph out, but I'm going to do this over again. Okay, so right now I just want us to, do we have any questions from here to here? No? Okay. And then the second most important thing is, can we get from here to here? Okay, let's not worry about the graph. So if you can get from here to both these sign lines, that's the most important thing, because everything else is just going to be kind of a recap from what we've done from the first quiz. So my goal for today is, can we get from here to these two sign lines? Because if we can, everything will just kind of fall into place a lot easier. Okay, so let me talk about the second derivative sign line. The way we can pull points of inflection is not the way we pull points of inflection off the original graph, right? Off the original graph, points of inflection are the transition points from concave up to concave down, right? But the points of inflection off the derivative graph are going to be located peaks and valleys. Okay? Because if you think about the original graph, if I'm looking at the original graph, points of inflection is going to be where the maximum steepness occurs. The maximum steepness is the place of the greatest slope, and place of the greatest slope is going to be located either as the highest positive value or the lowest negative value, so peaks and valleys. So you're going to pick out your peaks and valleys, plot them onto your second derivative sine line. And then we have to populate in terms of concave up and concave down. And again, this is confusing, I know, because you're thinking, well, this looks like concave down to me, this looks like concave up. But again, this is not the original graph. So the way you pull concave up, concave down, remember what concave up represents. Concave up, definition of concave up is where the slope is becoming more positive. So here, my slope is becoming more positive. So wherever positive slope occurs is where concave up occurs on the original graph. Wherever the slope of my f prime is decreasing is where concave down occurs on the original graph. Positive slope, concave up, negative slope, concave down. So once you can create these two sine lines, then there's no need to look at this graph anymore. Now we can build our graph purely based off of these arrows and these shapes, and our graph will mimic these shapes that these notations that we have in front of us. Okay. Okay, so I know that you may not have room, but I want to be able to sketch these graphs with you. So first, we're going to use this to sketch our f of x graph, because the arrows are going to match the shape of our graph, the pattern of our graph. One thing I want to highlight, that I want to emphasize is, you may be thinking, well, where do I put these order pairs, right? And the answer is it doesn't matter right now. As long as you can get your graph to show a relative min here, a relative max here, and neither here, it doesn't matter where it lands on the graph. But I'm going to make it where it's more distinct. So when I think of relative min, I think of a lower point. So I'm going to just pick a point that is relatively low in on my coordinate plane. Relative max, I'm going to pick a point a little higher. And then on neither, I'm going to pick a point that is somewhere in between. Right. So I'm just going to follow the path of my arrows here, but my concavity is going to be off. So I'm just going to do dotted lines. I know this is not my final draft here. So I'm going to have relative min, a relative max, flattens out, and then continues to go down. Okay, so there's my first draft of my function based off of my slope sine line. My second draft is going to be going back to this and then give it the appropriate curvature along the path of the graph. So now that you have your draft here, just go ahead and plot -3, -1, and 1 where it lands on the graph that you drew. So it doesn't matter where the order pair is. So find -3 on the graph. Where does the -3 land? For me, it landed right near the x-axis. -1, it landed here for me. +1, it landed here for me. So even if your location is completely different from mine, at the end, our shapes should match. All right, that's all we're looking for. Can we get the shapes? Are you able to match the correct shape? So these are nice target points now, because now we just have to give it the appropriate curvature from one point to the next, either concave up or concave down. So I want a concave up looking graph up to this point. Between -3 and -1, I want a concave down shape. Between -1 and 1, I want a concave up. And to the right of 1, I want concave down. Okay. And then the second thing I want us to do is to be able to sketch a second derivative graph purely just based off of these notations. So you're going to create an F double prime coordinate plane. Let's indicate what we're looking at. Anything above is concave up, anything below is concave down, anything on the x-axis are the POIs. So you're going to plot your point of inflection onto your x-axis. And wherever it's concave up, you want this graph to live in this region, in the above region, in the positive concavity region. So to the left of -3, I got to have it above, but these, I know it has to come back down to this point. So maybe something like this. Between -3 and -1, I want my graph to be located below the x-axis. So it's going to have to be down here, but has to loop back up, right? Because I have that point to kind of help guide where my graph's going to go. Between -1 and 1, concave up has to live in the above region. And then to the right of 1, concave down. So this is what I want you guys to try on number 4. Okay. I want you to label what you're looking at. From here, create a G prime sign line. And then from here, also create a second derivative sign line. And then we can create a picture of the G graph. And then from here, we can also create a picture of the G double prime graph. But first things first, if you can fill out these sign lines correctly, I think that's the biggest goal for today. If you can get that, then you've got the hardest part and most important part down. Okay, but I want to walk around and help you guys out so that we can get more comfortable with this. Sorry? Yeah. Okay. Neighborhood graphs, right? Positive slope, negative slope, slope 0. Right. Your X intercepts are going to go onto your slope sign line. This looks good. That's positive, but this is still also positive. This is positive. Yeah, so if it helps, encourage you guys to start here. Right, that way, I know it's confusing, right? You see that, you want to say negative slope, but it's in the positive slope region, so You want that first region to be rising. Right, so pick out your peaks and valleys. Those will be your POS. And then the negative slope is going to be counting down, positive slope is going to be counting down. That's the shading graph for the location. Oh, okay, right, yeah.
Yeah.
Okay, that was good.
Okay.
Where's your slope sign? You're there right now. So your slope sign, it's going to be that slope sign. That's good, yeah. But you don't want to look at the slope. So negative slope is going to translate to the constant down there. Good, at least there, yeah. This is concave down. This is concave up. I know it doesn't match with what we know, but it's because everything's different. But, Good. Good. All right, so your work looks pretty good. First step, find those X intercepts, right? These are slope zeros. So -2, 1, and 3, they're going to go onto your slope sign line. Now, look at the location. Don't look at the pattern, right? Look at the location. You see how this is in the positive region? That's going to translate to a positive slope. Between -2 and 1, don't look at the pattern, look at the location. All this is located above. Between 1 and 3, located below. To the right of 3, located above. Okay, good so far? Yeah, good. Second sign line, we're going to pull points of inflection off the original graph, right? Not points of inflection off of this graph, points of inflection of the original. So points of inflection of the original is going to be located peaks and valleys. So there's a POI, there's a POI, there's a POI. And then to pull concave up, concave down information, now look at the slope. Negative slope translates to concave down, positive slope, concave up. And then I encourage you guys to use these symbolic notations as well. I think it'll help because those arrows is exactly how our graph is going to move, and those curvature is going to be exactly how our graph is going to curve. Okay. All right, how are we coming along? So I think this is the hardest part. If you can get to this, I think everything else is going to feel well, I think we do need to practice a little bit more with the second derivative graph, but we can create the original graph based off of this and this. So create this graph first. So doesn't matter where your graph lives, as long as you can get your graph to be shaped like this. And then after you do your draft, then plot those points and then connect those points with the appropriate curvature. Okay. So try that, and then I'll go through the second derivative graph with you as well. Maybe you can use the space below to create your g of x graph. So, whatever your graph looks like, just make it where there's a relative max at 1, there's a relative min at 3, and there's neither at -2. Okay, so I'm just basing off of this graph, this notation here, right? So -2, I want my graph to flatten out. At 1, I want my graph to be some max. At 3, I want my graph to be some min. So I'm just going to kind of go through my graph with those properties. I don't really care about my curvature right now. I just as long as my arrow, my slope matches what I have in front of me, that's all I care about initially. Okay. So now I can improve this graph by involving or using this information from the second derivative sign line. So find -2 on your graph, plot that point. Sorry, over here. Find 0 on your graph, on your draft, plot that point. Find 2 on your graph, plot that point. So now between your highlighted points, you're just going to give it the curvature that we've already identified. Right. So concave down, concave up, concave down, concave up. Okay, how do we do? Okay, let's create a second derivative graph as well. So this may be a little bit harder, but we can do it. Mark off where things belong. You want the concave up to be located above. You want the concave down to be located below. You want the POIs to live on the x-axis. You know the graph has to go through all 3 points. We just have to know where to begin. Okay, where do we want the graph to live initially? To the left of -2, do we want to be above or do we want to be below? Below. The only way we can make it below and connect to that point is if it looks like this, right? That's the only way we can make that work. And then once you have that, then you can kind of just kind of loop through the graph, right? Between -2 and 0, above, has to come back down, below, above. Okay. Can we do one more? Because, you know, all this is easy, right? All this, you can just kind of pull that from, there's no effort here. It's just getting to this point is the hard part. Okay, so this is number 2 off of the more practice worksheet. I assigned this as homework, but I think we can just do it in class. So if you don't have it, just copy this down. Same procedure. I just wanted to get that practice. Can you create a slope sign line? Can you create a concavity sign line? Can you create a picture of the f of x? Can you create a picture of the f double prime? Okay, so start by labeling your graph. Create your slope sign line. Create your second derivative sign line. Okay, so your first goal is, can you plot those with critical points and with the appropriate slope and concavity? right, your sign lines look pretty good. Now let's see if we can sketch our graph here. So my first draft, I know I want a relative max at -4. I want a relative min at -1. And I want a max at 2. I go back and I find -2 where I sketched it. I find 1. And now I'm just going to work between those two target points and create the curvature that I want. Concave down, concave up, concave down. Notice I'm not going to complete that full concave down because it's still rising, right? So I just want to give it that arc, but it's still going to be rising the whole way. Okay, and finally, second derivative graph. We're just basing it purely off of this. Okay, we're not looking at anything else, just that. Concave up, concave down, POIs. -2 and 1. Okay, we start below, right? Above, below. Okay, how'd you guys do? Good? All right, good job. Tomorrow we'll do optimization. All right, have a great day, guys.
Mr. Yang,
Yeah.
I had a question for the f of x graph. At the point 2, it said the slope was going down. I was just confused why it's still going up.
Oh, wait, it should be going down, right?
Yeah.
Sorry. Yep. My bad.
Okay.
Thank you. Sorry, I missed that.
All right. Thank you.
Okay. Thanks.